Thank you everyone for joining the webinar today. It's going to be a doozy and we have a lot of material to cover. So the topic today will be about DeepSeek R1 and how it works, what it means, and what comes next. So quickly introducing ourselves. I am Eric, one of the co-founders and CEO of Encord. I'm joined here today by Frederik, who is our machine learning lead and has spent the last few weeks going through and really digging into DeepSeek R1, and he's learned a lot, which we're super excited to share with everyone today. So briefly, Encord is a data development platform for AI teams. So we help automate the process of managing, curating, and annotating at scale for teams that are building and using AI. And some of this will be relevant for the discussion later in the presentation. But we can kick it off with the agenda for the webinar, because again, right, there's a lot to go through. So again, the title of the webinar is DeepSeek R1, what it means, how it works, what comes next. By the end of the webinar, hopefully we should have all these questions answered. So what it means, how it works in more technical detail, and what we think the next steps are, and we'll include a demo as well and Q&A at the end. So going into the first question, what is DeepSeek R1 and what does it actually mean for AI? And I think what's interesting is that DeepSeek is almost like a Rorschach test for the AI world. So different people have different interpretations of what it actually means. And one of the most surprising things to me was the fact that it's an open source model, and they released the weights, also the paper and the methodology of how they train the model. And this is a positive development as far as I can tell. It really opens up the window into how these models work and allows us to have a better understanding and improve the operationalizing of these models. Now, whether this means that all new models going forward will be open source, and this is really the opening gate to the open source era of models, I think that's still too early to tell, but it's definitely a move in the positive direction. Another big surprise, and what a lot of people took out of this model, was that it was trained for only $5.5 million, which is an order of magnitude or orders of magnitude less than many of the other big frontier models. And there's some controversy around this number of whether $5.5 million was the real number that it took to train. I think that the best interpretation, at least from my side, is that it is a lower bound on the amount of money that it took to actually train this model. It may have been the number that, in terms of GPU costs of how it took to train the DeepSeek R1 model. But as you can see, and as we'll go through in the training methodologies, clearly there was a lot of iteration, a lot of thought, and a lot of hard work. And they didn't just get this at the first try. So it probably cost a lot more than $5.5 million to build this through multiple iterations, through the cost of talent, et cetera. But it is still quite impressive, the quality of the model that they were able to produce for much less than many of the other research labs. And we'll get into why we think it was cheaper a little bit later in the presentation. Another lens by which people use to look at DeepSeek is that it is a gut punch to the market, specifically to NVIDIA, but also to OpenAI and some of the other frontier labs. It took hundreds of billions of dollars out of the stock market, which is quite impressive as well in its own right. Personally, I'm not as bearish on NVIDIA from this news, but this is not financial advice, and the market is always right. I think ultimately, these models coming out and proliferating probably means there's going to be more demand for compute in the long run than less demand for compute. So that, I think, is also a debatable point. And the final big frame for this is the geopolitical AI arms race that supposedly it has started. So some people are interpreting this as a warning shot, or as the first shot of an AI arms race with China. Again, I think still early to tell, and that is a debatable interpretation. So all of these, I think, are quite interesting, but miss the main point. And I think that the actual main innovation here of what this model means for the AI world. And that is that DeepSeek R1 is really marking the transition from the train time compute age to the test time compute age. So previously in the last few years, the main method that we had to improve these frontier models was to throw a lot of training data at it and a lot of compute at it, and to have this kind of pre-training phase as the main time lapse by which the models got better. But what we're seeing now, and what I think the big labs have already discovered and been working on for the last months and years, is that the new method going forward to improving these models' performance is actually test time compute. So compute that you run at inference time to allow the models to think for longer and to get better results as a function of that. So DeepSeek R1 is not the first test time compute model, of course. There's the O1 series of models, but because it's open and because it's made such a splash, it really is a definitive stamp that it can chapter this new era of AI into the test time compute phase. So I think that's the main thing that I got out of it actually when I was reading the paper and seeing the release. So what does this train time and test time compute actually mean? And I think if we go back to neuroscience, it really helps conceptualize what this is. So there's a famous book, Thinking Fast and Slow by Daniel Kahneman, and it outlines two ways in which humans think. One is system one thinking, and this is the kind of automatic response that you have when you're thinking about things. Often regular speech is the system one speaking, is kind of flowing thought, flowing words. And then there's system two thinking, where you sit down, you kind of think through things logically, you put more effort to it, and you might get tired after doing too much system two thinking. Think of a math exam or something like that. And so far, the frontier models of up until now have mostly been of this system one kind of variety. They're effortless in a way. They're just trying to predict the next token. So they're going from token to token, and it's almost like they're operating out of intuition. But this regime shift to these test time compute models is more along the lines of a system two kind of way of thinking about the world, where the models are going through a path, deliberating, backtracking, and going through some of the steps that humans actually take when they're properly reasoning about things. So the system two is actually what's going to be dominant, at least in the next era of models, as these reasoning models come out from DeepSeek and from others. And to really highlight this, we have an example here. So in a second, I'm going to read out a question, and I want you to read the question and then first immediately think, what is the response? And then to take a moment and actually read the question again and try to answer again. So try to answer this in two ways. Just after you read it, what do you think the answer is? And then pausing for a bit and then trying to reason through the answer again. So if we go to next slide, the question is, a bat and a ball cost a total of $1.10. The bat costs $1 more than the ball. How much does the ball cost? So think for a second and then pause and think for a little bit longer. All right. Hopefully that's enough time for most in the audience. The interesting thing about this question, and it's often used in studies, is that the immediate response that people have, the intuition around the question, is that the bat costs $1 and the ball costs 10 cents. Because you see a dollar, you see 10 cents is a dollar more than the ball. But of course, that doesn't make sense because then that would add up to more than $1.10. And if you go through and do the math and think about it carefully, then you'll see that the correct answer is that the bat costs $1.05 and the ball costs 5 cents. And we'll see later in the presentation how a model like DeepSeek actually thinks about a question like this. But this really crystallizes the difference between your kind of system one brain and your system two brain, which again, system one is the ChatGPT-4, and the system two is the DeepSeek R1s, the O3s of the world. All right. So one other interesting kind of delineation of this kind of system one versus system two type of model is looking at the actual performance. And DeepSeek is a very performant model as far as the benchmarks that have been published. And the bars to look at here are actually the blue bar on the left of each set and the blue bar on the right. So the blue bar on the right was the DeepSeek V3 model, which is one of these kind of system one models, like trained in this kind of normal train time compute pre-training era. And the bar on the left is DeepSeek R1, which uses this kind of system two, more reasoning, reinforcement learning based approach. And you see that it's much better, even though the core architecture, the base of the architecture is actually the same, as we'll get into in a bit. So if you really just kind of sit down and think about a problem for longer, you will get better results. And one of the other impressive things about DeepSeek R1 is that it is actually quite performant as a model, and it compares to some of the top models produced by the research labs, notably OpenAI and these O1 models. There is a caveat, however. Perhaps DeepSeek is not that great to use in the sense that there have been some reports of data leakage. So the company Wiz found a lot of data, like a leak of data from the DeepSeek model, exposing up to a million records of user data. And there are some questions around potential monitoring or censorship in the model. As we can see in the video here, someone is writing a question. They're running it. It starts to answer the question, and then it's just pulled, which is not what you see in normal chatbot behavior. So it implies that there might be something kind of under the hood here, which brings up some questions of using DeepSeek, at least the hosted version of it. Of course, it is open source, and you can run it in your own servers, and that mitigates some of the current concerns here. But it is one of the potential issues. So that kind of takes us through some of the items of what DeepSeek R1 means. It's a mover of the market. It's the beginning of the open source era. It's a challenger to OpenAI, but more than anything, it's the beginning of this transition to the test time compute era, which I think we'll see a lot more of in the coming year. So now I want to transition this over to Frederik, who will go over how DeepSeek works in more technical detail and share some of the learnings that he's gained from actually experimenting with the model.
Yeah, thanks, Eric. Thanks for the very nice intro. I think it's going to be tough to me to follow. Yeah, so what we'll do now is we'll have like a deep dive into how this thing actually works, which is we will first look at like how this kind of system two thinking it actually looks in practice. Then we'll go into the algorithm that they employed to actually achieve this. And then finally, we will look at how the data for such an algorithm will actually look and how they came about actually getting the data. We do take Q&A. I just saw that in the chat. We have a slot for that in the end, by the way. Okay, so let's just dive right in. So let's have a look at how this reasoning kind of looks. And so I brought in, I asked DeepSeek the same question as Eric asked you guys a couple of minutes ago. And this is essentially what it answered. So what you will first notice is that there's this think tag in the beginning and an end think tag in the end. And in between is essentially what is DeepSeek Scratchpad or DeepSeek System 2 thinking. And so one thing which is new from DeepSeek is that we can actually see the reasoning going on here, which is not the case for instance, OpenAI's models. And so typically what happens, at least from my experience, is that we'll see something along the lines of this type of situation. So first of all, it'll somehow summarize the task it was given. So here it says like something with a bat and a ball and the cost, and I have to figure out what the cost of the ball is. Then it'll try to do some sort of derivation in terms of finding the solution. At some point it reaches some sort of a conclusion, and then it'll try to self-check somehow. So just to make sure I didn't confuse myself, and then it's going to go on for even longer and trying to check its own answer. Then it'll try a second approach just to make sure that if it follows different paths, it should reach the same conclusion. And eventually it sums everything up into a conclusion, and then it gives the actual response. And one thing which is really remarkable here is that all this stuff, all this sort of taking things and trying to approach it from different angles, doing self-checking, these kind of things, it's not that the developers of the model, they impose this on the model by biases or by a particular training paradigm, except from the fact that they said you're supposed to have a thinking session, and that was essentially it. I think one way of showing it is this graph. So this is from the paper, and what they show here is a graph of how long this thinking session was as a function of the training. So on the x-axis we have training steps. On the y-axis we have the average length of this thinking session, essentially. And you can see that while the training progresses, the thinking session just gets longer and longer and longer, and it doesn't even seem to tail off, right? It's not clear what happens when you keep training, if it's going to keep making the answers longer. But essentially, this is sort of illustrating this sort of self-emergence of reasoning, and of actually breaking down problems and trying to reassure yourself that you have the right answer before you actually answer. So I think that's like really cool and very remarkable. Okay, so this is essentially like saying that this is system 2 thinking, right? At least conceptually. And I don't think there's any way around it. I think we need to look at this GRPO algorithm that everyone is talking about, or group policy optimization. And it has this ugly equation. If you're used to looking at these reinforcement learning equations, it might not be that ugly again. But I am like a very practical-minded person, so I like to think about it in code. So in a minute, I'll show you roughly the same thing, but in pseudocode, and then I'll help you break it down. So don't pay too much or spend too much time looking at it right now. We'll get back to it. But before I go into that, I want to take a moment to just acknowledge some of all the other things that we won't have time to cover here. So the DeepSeek team, they were very limited on resources as compared to OpenAI, for instance. And that has caused them to have to find ways through that are different from what we have seen in sort of literature and like in the field in general. And one of the things that we have heard rumors of, about, at least I haven't seen it in the paper, but we've heard rumors that they, for instance, had some GPUs that were much lower capacity than, for instance, an H100. And so they had to go down to the assembly level of the CUDA kernels to actually program something that is super, super fast and works really well. And couple that with also something called latent attention mechanisms, which is essentially a way of spending less memory and a bit more compute to get almost the same capacity as original sort of attention layers, which is another just like effect of the fact that they didn't have the resources to just spend the memory it was required to train it on a lot of GPUs on huge clusters. And finally, another effect of that is like this mixture of experts approach, where they trained this almost 700 billion parameter model, but it's not actually running inference on all the parameters when you're getting an answer. It's actually running only on a subset where it has a very smart mechanism for choosing the right experts conceptually to answer the question. So it's just like some of these things that they had to do to make it work on a low budget, which I think is really cool and what really pushes the field forward. So again, as Eric said, it's like if you put your head down, think carefully enough about a problem, then these sort of new solutions that will work really well, they will emerge. Okay, so let's get back to this GRPO algorithm for a second. So I wrote it out here, and before you spend too much time reading it, I'm gonna step you through it anyway. And if you are not like a technically minded person, you can spend 3 minutes, grab a cup of coffee, and I'll wake you up in a bit when I'm done. Otherwise, sit tight. Okay, so that big equation, it basically meant something along these lines. First of all, when you're doing this reinforcement learning training, the first thing you want to do is you want to average your loss or your objective over a lot of questions. In this situation, the questions are math questions, coding questions, and in general, things that you can verify programmatically without any deep learning system. So a math question is nice because when you ask the question, you know what the answer will be. And code, you have compilers and you can run unit tests and all these kind of things to actually compute a reward deterministically. So that's really, really nice, and that's a thing we'll get back to in a bit. Okay. Second thing is that you need to average over a bunch of answers. And that's where the group part of the group policy optimization comes from. You're going to compute a group of answers from one model. You've probably seen this temperature parameter when you're running something against these models. So you can sample multiple different answers from the same model for the same question. Now you're going to average over those as well. Okay, and then you're going to compute some rewards. And they are these deterministic functions. And after that, you're going to standardize them. And standardization essentially means you're going to make sure that if you compute the mean of all the rewards, it's 0, and the standard deviation will be 1. And so what this effectively means is that the reward will be higher than 0 whenever the answer is better than the average within the group. Okay, so keep that in mind. Then the second thing is that you're going to take your, I guess if you're used to thinking about reinforcement learning, you know that there's this thing called a policy. And you're used to keeping track of two policies, the old one and the new one. So here you're going to score all the answers based on the old policy and the new policy. And then what you're going to do is you're going to compare them. And essentially what you want is that for the right answers, you want the new policy to have a higher quality score than the old policy. So that's what we're trying to get to here. And you're just going to compare them by saying, by looking at the relative difference. So what it means is that whenever the relative quality is higher than 1, the new model favors this answer more than the old model. So that seems like we are on the right track. Then you multiply this relative quality with the reward, the standardized reward. And so whenever the reward is above average and the relative quality as assessed by the new model is better than the old one, then we're in a good spot. And that's essentially what we're trying to optimize. And then there's one little thing more, which is we have this thing that if we just do this naively, it might get very, very exotic and start doing weird things. So we just want to make sure, like keep it in a leash, this training process. And that's why we have this distance from what we're learning to the base model where we started off from, because that base model has some properties that we don't want to lose on the way. So that's essentially what this group policy optimization does. And now is the time for those of you who are not technical to wake up again, because there are like 2 key takeaways here. The first one is that these reward functions that we're talking about here, they're deterministic. They need no human ranking, for instance, if you're used to thinking about RLHF. So no humans involved, which is very nice because then you can move things much, much faster. Right? You don't need to wait for humans to annotate things. You can just ask the computer and get a response immediately. The second thing is that there's no critique here. And the critique is essentially a neural network that tries to predict the value of every token that the model predicts. And we don't need this in this particular setup, which is nice because it essentially halves the resource requirements. And that's one of these effects of having a low budget. You cannot afford having both a model you're training and this value model that is as big. So if you had like 2 times 700 billion parameters, right, it would require much more resources. So really, really cool. And this really lowers the barrier of entry for these RL techniques. Okay, so that's what I wanted to tell about the training process. So it's this reinforcement learning thing where you have deterministic functions that essentially reward your model, and then it tries to get as much reward as you can by optimizing or maximizing that objective. Great. So DeepSeek, they actually employed this, and they got a model already. They call it DeepSeek R1 0. And already with this model, no human labels or anything, they actually managed to perform on par with O1 Mini on this very low budget. But and even we saw this like self-emergent reasoning thing, which is really, really cool and exactly what they wanted. But it has some limitations because, for instance, the model just started mixing language. So it's trained on Chinese and English language. So it started just mixing these things. And that basically made it less aligned with human preferences and what humans would like. So they had to do something about it before they could put it into the public if they wanted people to also use it. And that's what we're going to dig into next. Okay, so now what I'm going to talk about is the data for this problem. And I'm going to show you a graph gradually. And every time I draw this rectangular thing, it's going to be a model. Every time I draw a square, it's going to be a training process. Every time I draw a circle, it's going to be more data you put into the process. Okay.
And just
So
for clarity, this is moving from the DeepSeek R1 0 model, which was trained just purely with reinforcement learning, to the DeepSeek R1 model that we all now know and love. So how to get from one to the other.
yes. So how do we get from reasoning but not good at reasoning but not useful to good at reasoning and useful? Okay, so that's the goal. So the first thing they did was they took the model they had already, because it was good at reasoning already. So they sampled a lot of chain of thought examples from that model based on all the questions they had. And then they employed a lot of, I don't know a lot, I don't know how many. They employed humans to actually curate the data and clean it such that it could be used for training a new model. What they then did was they took their DeepSeek V3 base model, and then they used sort of traditional supervised fine-tuning on this new chain of thought data. And the reason why they did it was to sort of give this cold start model a head start, because these reinforcement learning techniques, they are very sort of unstable in the beginning until the model starts to figure out where the reward is. So this gives it sort of a head start. Okay, so it knows about reasoning now, but it's not good at it. So the next thing they did was they said, okay, we had this language inconsistency problem. So we're going to use the same reinforcement learning algorithm, but this time we're going to add an additional reward function, which basically measures how much does this language mixing happen. And the more it happens, the lower the reward we're going to give. And so this basically gave them another model, another reasoning model. And I call it DeepSeek R1 1, just because it doesn't have a name in the paper. But it's still not really useful because it wouldn't follow instructions and these kind of things. It would just solve math and coding problems, but in a consistent language. So then again, you need to think about, okay, how do I solve this? How do I, make it also follow instructions and these kind of things? And what they did here was, again, they took the model they just trained. It's even better at reasoning, and so they generated even more chain of thought samples that they could use for the supervised fine tuning. And they used techniques like rejection sampling. They even used their old DeepSeek V3 model as a judge to select the good samples. So again, try to bootstrap this data problem as much as you can. Use them as many models as you can, and only bring in humans when it's necessary. Furthermore, they took a lot of, a lot, it's not a lot these days, but they took 200,000 samples of non-reasoning data, so sort of traditional instruction tuning data. And then they added that on top. And then again, same idea, take a new fresh base model, do supervised fine tuning to give it a head start. And now it's almost time for the moment of shine. So the last part they did was, well, they knew that they had to align it with human preferences as well. And again, from their history of training other models, they could bring in some of their data from these RLHF flows they had been doing previously, and put it into the reinforcement learning. So same algorithm, but an additional reward this time, which is this human preference reward. And then training with reinforcement learning eventually made them reach this DeepSeek R1. And so the reason why I really wanted to bring this story forward because I think it's underappreciated on what you see on socials. And I think it's a really good sort of illustration of how far you can get by just bootstrapping your data problem, getting high quality data and doing it as efficient as you can by using all the models you have available, both those you trained on your own, take data sets you can find somewhere else, take models from Hugging Face, and employ them as a service to your data problem, and only bring in humans when you need it. So I think this is like a really cool story, and it's like very parallel to what we've seen in, for instance, many of these video generative models, or with SAM 1 or 2. They also had these sort of data engines where they bootstrap their data problem with previous models and other models. Great. So I think taking all this sort of into account, that's most likely why DeepSeek has been able to produce something that is so cheap as compared to everything else. Had we done this webinar a week ago, we wouldn't have had this column with O3 Mini. It's just been released, and at that point in time, DeepSeek R1 was like 30 times cheaper than O1, which I think is very remarkable, and it's exactly because of all the tricks and engineering they had to do in order to make this work at a low budget, which I think is quite remarkable, right? Train it for like less than $6 million as compared to probably more than $100 million from OpenAI. Yeah, so I think it's a really, really cool story. Yeah. So, okay, so I think this is a really good point in time to actually put it to the test, right? And what we decided to do was say, okay, first of all, we want to test it on something else than math and coding, because we know that these two areas are something that it was actually explicitly trained on. So we want to see if we can make this reasoning stuff work for other use cases. And what better test than actually running it through Jeopardy? So a good Jeopardy expert would probably get like 65% correct when asking questions in Jeopardy. So the goal was essentially to beat that. And then, of course, we also want to sort of have a look at this reasoning capability. Can we somehow have the model reason about its own confidence? So that's what we set out to do. And what we used was this DeepSeek R1 32 billion. So it's a chapter I haven't even opened, which is distillation that they also employed. So if you're interested in that, let us know, and we are more than happy to do another webinar on that front as well. Great. So in Encord, we define data projects for machine learning or AI development via what we call workflows. And this is a sort of classical example of a workflow. And it essentially governs how data is supposed to flow through the system. And every time you see a purple node, it's an agentic node. So it's a node where we can have automation running. Every time you see a red node, it's where we will bring in humans. And so this particular flow, what it does is that it takes Jeopardy questions, route them through DeepSeek, ask DeepSeek to essentially fill out the table, if you imagine Jeopardy, which is you have this table where you have points from 100 to 500, and you have 5 different categories. You have question and answers. So we're going to give it the question. We're going to ask it for the value, for the answer, and for the category. And then we're also going to ask it if it's confident or not. And whenever it's confident, we're going to send it directly to another data agent, which is a data transfer agent. And what that agent will do is that it'll read off whatever it predicted and store it in my local DB on my local machine. And then in the end, what we'll see is we'll see the results. And now, when it's low confidence, it'll route it through a manual correction and review stage where a human can be brought in and do the corrections before we pass them on. Okay, cool. So now is this switching thing where I have to share something else.
So we'll be seeing some Jeopardy questions go through the DeepSeek model and then through the subsequent workflow and see what that actually looks like.
Yes. Okay. So what we are looking at right now is some answers already predicted by DeepSeek, and it should be updating sort of as we go. So you will see new questions pop in once in a while in the top. And what we basically see is like there's a question, there's the true answer, and there's the predicted answer. And then there's the true value of the question and the predicted value of the question. And so you can see that in some situations, DeepSeek actually gets it right. So a blow with a whip, it's lash, and 200 and 200. And other times it almost gets it right, but maybe gets the value wrong. So this system is running live, and it's happening completely automatically. Yeah, and so I thought since there are probably some machine learning engineers out there, why not take it to our loved Jupyter notebooks? So here I have essentially a TV kitchen show of actually using the results. So I prepared a little script that reads from the database and exports all the predictions to a CSV file. That's what is happening here in this first column. And then we can use the CSV file as we're used to. We can just import pandas. We can read the CSV file. We can print how many answers we have, and we can display some of the answers as well. So this is the same table as you saw before. And already here, it's nice because now we can do all the sort of traditional things that we're used to do with pandas. And I think the first question we want to answer, right, is like, how good is it? Will it actually perform better than these 65% that I mentioned? And so one thing we could do is we could take the answer column and do a string comparison directly to the predicted answer and see how often that goes right. And it goes right in 41% of the times. Okay, so it's not quite 65% as I was hoping. So yeah, that's annoying. But I also print some of the situations where it's not correct. And this gives me some hunch about the performance of my accuracy metric, essentially. So if I have a look at this one, for instance, it says the FBI, and over here it says the FBI, which is, I guess, the same thing, but just a couple of dots. And there are multiple of those. So maybe there's a better way to do it. And so what we did just for this exercise was we took some small text embedding model from Hugging Face, and we can compute some embeddings for all the different answers and for the predicted answers. And then we can do a similarity score. And then we can select everything which is above 0.5 in similarity. And you might think, okay, is that really fair? So, sorry, I'm scrolling now. I'm going to stop here. So I sorted all the scores. They're over here on the right column. And let's have a look around 0.5. So this is not right. This is not right, but this seems right. Slippery seems okay. Not good. But if I go above it, there are also some that seems all right up here, right? The FBI one, for instance. So it's like a blow of a wind, I guess.
So basically, the lower bound for the accuracy is 40%, and with this additional method, the upper bound is something like 70%.
Yes. So it's somewhere within that range.
And a good Jeopardy player, someone that would be quite competitive in the game, would be probably around 70%. So DeepSeek is probably between an okay Jeopardy player to a good Jeopardy player, at least with this model and this interpretation of the results.
Yeah, and then of course the other thing that is interesting, or maybe I need to make this a bit smaller, is the reasoning component, right? Which is like whenever this like DeepSeek says, I'm not sure about the answer, is it then correct what it's saying? Is the answer then wrong? And so I did like a quick sort of check on that as well. And if I look at all the stuff that it's answered so far, I found that 4% of all the answers, they were predicted to have a low confidence. I found that 25% roughly were answered where we couldn't pass the response, so we couldn't sort of match it to what we were expecting. And I found that 70% of the answers were with high confidence, and it's of those 70% we've just been looking into the accuracies. And I just brought in all the answers that for which it said it was very unconfident or had low confidence, and they are certainly not right. So they're very far away from whatever the true answer is.
So this is very important because one of the issues with a lot of the LLMs and chatbots of today is that they don't have a good sense of when they're being overly confident or not. And what it seems an indication here is that with this reasoning model, it can kind of reason about its own internal knowledge of the world enough such that it can say whether it's certain or not, which actually would be very, very useful for a lot of practical applications, at least in this experiment. Is that a fair assessment of this?
Yeah, I think that's exactly right. Another way to put it is that its precision is very high when it comes to confidence, but its recall is rather low. Yeah. So I agree. Yes. Okay. I think it's a good time for me to switch back to the slides. They are here. 1 second. There we go. Okay, so this brings us into the last piece of the webinar, which is what have we learned and what comes next. And there we go. So I thought it would be good to just bring up some of the immediate limitations of DeepSeek R1, which is when you're developing up against it, it's rather hard to use. Actually, I think one fun little anecdote is that I did a similar exercise for O3, and it took me roughly 20 minutes to build the agent, but it took me like 1.5 hours before I got all the stars aligned for just passing the outputs and making sure that it followed the instructions that I wanted it to follow. So it essentially tells that there is some maturity to be reached here. Another thing is that it's text only right now. I think it's the same for O3, but these reasoning models will probably also. It's not hard to imagine that they will work for multimodal problems as well. And I think I actually also saw some language mixing still. But I think what's worth noticing is that in the paper they actually address all the things that we realized was wrong. So they say, oh, we know the function calling is missing. We know the JSON outputs are missing. We know that it's still doing some sort of language mixing once in a while. We also know that it's very sensitive to the prompt engineering, and we know that it's not super good for software engineering yet. So this is essentially saying we know we cannot plug it into Cursor quite yet. And all these things they're working on addressing already. So the picture will change really, really fast. Yeah. So those are sort of some of the more immediate limitations. But all this will come very, very soon, I'm sure, and we'll get to love it even more. Yeah. Now, also in the interest of time, here are the conclusions of today's webinar. So first of all, I think as Erik also sort of really underlined, test time compute is definitely here to stay. We've seen it here. We've seen it with O1 and O3, and also in other domains, by the way. And DeepSeek has really lowered the entry barrier for reinforcement learning. We saw that we don't need nearly as much human involvement in actually building the data sets for training these types of models. And we also saw that they found an algorithm that puts much less requirements or restrictions on the compute resources you need. Another thing is that this data engine is really, really key for all these different projects. You need, if you want to be the best in the market, you need to find ways of bootstrapping your data problem such that you can reach the goal faster. And that's what they have excelled in here. That's what they have excelled in with the SAM project, and so on and so forth. And then, of course, use humans only as a last resort when you cannot do it with other means. Now, the final thing is, of course, that this is just the beginning, right? Usability will improve. I've even heard rumors that the version will also drop soon. And I think it's not super hard to see the methodology extend to many other problems and modalities as well. Yeah. You have anything to add here, Erik? I don't know if I missed anything before we go to the Q&A.
No, I think that's a really interesting summary, and also the fact that there are clear limitations that we ran into, but they were all listed in the paper, and they're working on all these things. So really, we're seeing still the early days of this DeepSeek series of models. So I'm very excited to see what else they'll come out with next in this kind of test time compute regime. So I think we're right on time, but there are a couple of questions in the chat that we can go through. So one question here is, when DeepSeek says thinking, does that mean it's applying active learning to check the most appropriate point to check before showing results?
Yeah, it's a good question. So in one sentence, active learning is when you select the next batch of data to train on. And that's not what we're seeing here. What it does here is it's I guess, true reasoning, if you will, which is kind of different. Is that a fair answer here, or did I miss something in the question?
I think that's a fair answer. Active learning is kind of a train time type of strategy, whereas the reinforcement learning and the process, the chain of thought process that DeepSeek uses is a test time strategy. And I think it's not a question, but one, I think, interesting observation in the chat as well is test time compute. This is how we do our thinking every single day. And yes, that is true. The one caveat there is that that's how we do our system 2 thinking. Still, a lot of our system 1 thinking is quite automatic, and it comes without much reflection. You move your hand or you say a word, and sometimes it just kind of flows, versus trying to solve a math problem that is thinking in a way similar to how the DeepSeek and likely the O1 models are thinking as well. So I think we're slightly over time, but really appreciate running through the technical details of DeepSeek and through the demo and the experiment. It's quite fun to see how DeepSeek fares as a Jeopardy player, and that it can also reason about its own ability to answer questions. I think this is a kind of underrated quality in the model, and we should see more of this from some of these new models coming out. I think would help in a lot of really practical use cases. Please join us for our next webinar, which will be about physical AI and streamlining computer vision and data creation and labeling for physical AI. So thank you everyone for joining today. Really enjoyed the questions and comments in the chat, and we'll see you at the next webinar.